Today we're going to look at how we model the sound capabilities of this thing, the Sega Mega Drive, or Genesis in North America. We're not the only ones who have done that, obviously, but we worked very hard on it, and I had to create 4 different hardware setups to test various things and be sure we got some things right, and I think it's going to be interesting, so please stay with us. We started our Yamaha OPN series emulation quite a few years ago with the OPN, and then we went to model the OPN2B, and the reason was simple. Both of those chips have digital outputs, which we know how to capture and compare. See, the OPN2 in the Mega Drive outputs its audio directly in analog, using a very crude multiplex 9-bit DAC, and this means that each of the 6 voices are sent out on the same DAC one after the other. This is quite similar to the OPLL, which you can see in my previous video. So anyway, the OPN2 is pretty ill-suited as a chip to start making a bit accurate emulation. Not only its multiplex signal is pretty weak in terms of amplitude and width, it requires quite a bit of amplification to raise it to line level, and it's not trivial to do that without picking up tons of noise from all the digital junk in and out of the chip. The OPN2C is slightly better, but it still outputs on a multiplex stack. The big eureka moment was when I found out about a rather obscure OPN2 variant, the OPN2L, which is used on the Fujitsu FM Towns 2, which was supposedly backwards compatible with the OPN2, but this time with a clean digital 16-bit stereo output. So I got a few of those and created this little board with the 3 main discrete variants of the OPN2 on it. Essentially, it's just an automated test rendering setup powered by a Teensy and a micro SD card. All 3 chips are clocked by the same external 8 MHz clock, and the Teensy write are sent to all 3 chips simultaneously. So I felt it was an ideal benchmark to be able to get synchronized renders out of the 3 chips for comparisons. The word signal at the start is actually some clever form of synchronization trick. The internal counters of the OPN2 for the LFOs and the EEGs are free running, so instead of trying to force resync them, we just try to figure out in which state they are in by doing this little pattern there, and we figure exactly the cycle at which they are, and we apply those values directly to our emulation counters for them to match. Sampling both analog chips at 10 MHz and the digital one at 20 does take a load of memory. Each test takes upward of 8 GB of raw data, which you can see here. In order to make this data usable, I coded something to convert this into a 3-channel 53 kHz wave file, with the serial digital stream for the OPN2L being done bit accurately, along with the synchronized discrete analog values of the 2 other time to the clock output of the OPN2L. So this is our test 9 here, and you can see it outputs quite a complex waveform. When scrutinizing the data, it's kind of obvious that the 3 chips are essentially doing the same complex calculations, especially in terms of like frequency content and actual FM processing, even after many seconds past key on. So this gave us confidence that we could base our EMU core on something concrete and get bit accurate result, well, at least for the specific test we created, all 40 of them. With the digital stuff out of the way, we now have to put the dirt back into the system, so this is where this little EEPROM card comes very handy. So this is where the test ROM comes from. We coded a little ROM in 68K assembly that does a variety of tests. A few things can be gathered from this, but the 2 important ones is an impulse response of the whole chain from the point where the audio leaves the OPN2 up until the front headphone jack or the back mono output jack. And the main reason we did that as a ROM is that it was a convenient tool to share with other Genesis fans, like Kevin Arberg, who owns 10 or so different Genesis models and was kind enough to provide recordings for us. So is this related to Artemio Urbina's MD Fourier? Well, yes and no. MD Fourier is an analysis tool. It's designed to catch the differences between a different system's frequency responses by analyzing and comparing various recorded tones, and it works great for that. But since we just want to copy the filtering behavior of the circuit, we can go with a simpler but equivalent solution. If we assume the whole circuit is a linear time invariant system, then all we need is its impulse response. For that, we use the OPN2's 6th channel set to DAC mode. By forcing the DAC to do a large sudden jump, we get the step response of the system. Then we can easily mathematically convert that into an impulse response, which then can be fed to a FIR filter, reproducing the filtering of the circuit on our sound source. Specific DC tests are done also to pick up the audio directly from the pins using a DC coupled scope. This highlights the famously non-linear DAC of the OPN pretty well. An ideal 9-bit DAC would sound like this on a decaying sine wave. The quieter the level, the less discrete values it can use. But on early models of the Mega Drive, it sounds more like this. What? Due to the way the DAC is implemented on the die, there's a huge DC voltage jump in the output when switching from index value -1 and 0, or 7F and 80 in hexadecimal. This test also allows us to capture the relative levels of the SPSG DAC as well, which is a separate, different generator in the Mega Drive. The third setup uses a modified Mega Drive PCB. The Z80 is replaced by my very own ICE80 board. The PCB is permanently stuck in Sega Master System backwards compatibility mode by a switch, and since the Z80 has no known way to toggle the YM2612's chip select pin in SMS mode, well, I kind of hacked the cable from the one unused pin of the ICE80 board directly to it. With the 68K basically stuck in a permanent idle loop, I can drive the video in either Sega Master System or Genesis Mode 5 graphics and write to both sound chips. So I ported our VGM player to ARM, and I can play any VGM or VGZ file from the mini SD card. It's very nice to be able to compare complex mixes of sound, and for tests that use both the OPN2 and the SPSG. Last, and as seen in one of my other videos, I created a YM2612 cartridge for my perpetually in-dev Famicom Base MIDI synthesizer. This can connect directly with the chipsynth MD interface, and I use this for various confidence tests. Hey there! Nice. So now I have the OPN2C on the cartridge. So this is supposedly the clean one. This is just the hardware. Kind of bit of dirt there. And that's just the emulation. Both at once. Boink. Quite easy. Let's try something else. We're gonna go to Oregon. It's kind of low. Let's make this alias a bit, because we do love aliasing. Nice. T. See, the spectrums wouldn't match and wouldn't sound remotely similar if it weren't for the fact that we emulate the chip at 53 kilohertz, well, each channel at 53 kilohertz. It's not that simple because we do the multiplexing as well. What else? Let's try the SSG stuff because I love some SSG. It takes a while for the buffer to flush on the device. And it slows down depending on which octave you are. So that's how SSG works. It's perfectly matching patterns there, although they're not perfectly timed, and that's the reason why. It's because the chip has an internal clock that's different from my emulator, of course. But if they're a clock at the same master rate, their internal stuff is not the same, but their pitch is going to be the same, if that makes any sense. Last, before I swap the cartridge, would be going to do this ladder test here. Wait a second. There's a bit of that because it's a 9-bit DAC, kind of. It is a 9-bit DAC, but it's kind of tweaked in case of the OPN2C. That was the, I don't know if you're going to see it, but it's the YM3438. Now I'm taking the 2612 inside, and it's going to be way more noisy. Bit of junk there. It's probably just due to my poor analog design on the cartridge. It's Rev 1. Now I need to resync it again, and I'm gonna follow it by setting myself the same model. So now with the same patch loaded, I should get some nasty effect. Yeah, I need to match the volume now. Come on, die already. So that's it. Just takes a long time for the decays to really end up. It's always fun. Okay, tired of that. Let's fuzz it around. This is awesome. SSG, try to do that with the DX7. Totally awesome. That's one of the cool things about the product, is that I could just be there on my own and hit random and still be excited by the thing. Sorry, Mom. That's more typical FM. Trying to make a song with this. It sounds like typical sword clashing in rah 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 rah. So anyway, I hope you liked it. So if you liked this video and you want me to make more, the best thing is really to buy a license of our software. We do everything we do out of pure nerdy fashion, and we want to do that as long as we can. And especially, that might interest you, the next things to come out from Plug are going to be this guy and that guy, so you wouldn't want to miss it. And also, please subscribe. Thank you.